Let's jump right into this explainer for Chapter 10 of our complete C programming series, where we are tackling file handling. We've been building our C programming skills piece by piece, and today we're unlocking a massive new capability.
We'll kick things off with Section 1, the volatility problem.
To really see why file handling is an absolute must, let's take a quick look back. In Chapter 9, we learned how structures brilliantly organize our data in RAM. We could finally group a student's name, their ID, and their grades into one neat, structured block of memory. It was like having a perfect, lightning-fast filing cabinet right there while our application was actively running. But here's the catch. RAM is entirely volatile. Think of RAM like a whiteboard. It's incredibly fast and perfect for jotting down ideas while you're working. But the moment your program terminates, or if the power simply flickers, that whiteboard gets completely wiped clean. All of that meticulously structured data just vanishes into thin air.
So, the real problem we have to face is, but what happens when the program closes? All that data disappears. Imagine building a program to manage bank accounts, and the moment you close it, every single balance is erased. That's exactly where file handling comes in. File handling acts as a permanent bridge between these two worlds. It literally lets us grab data out of our temporary, volatile C program in RAM and write it into a permanent file on your hard drive, so it persists forever. And of course, it lets us read that data back into the program whenever we need it again. Moving right along to Section 2, what is a file?
At its core, a file in C is elegantly simple. It's really just data stored on a storage device that our program can actively talk to. And by talk to, we basically mean our code can perform two primary actions: reading content from the file and writing new content to it.
Now, you are primarily going to deal with two types of files depending on what you're building. First up, we have text files. These are human-readable files like your .txt documents or your .c source code. They just store standard text characters. On the flip side, we have binary files. These are machine-readable, like a .jpeg image or a .dot file. They store data in the exact binary format your computer uses in its memory, which makes them way faster for the machine to process. Because they are fundamentally different, C gives us specific functions depending on which type we're working with.
All right, Section 3, opening and closing files.
It all starts with the file pointer. You declare this using a capital F-I-L-E, an asterisk, and your pointer name. This file is a special structure defined in C that holds all the behind-the-scenes information needed to interact with the file on your disk. Honestly, the easiest way to think about this file pointer is as a physical wire connecting your running program to the document sitting on your hard drive. Without this wire, absolutely no communication can happen. Once we have our wire, we need to plug it in. We do this using the fopen function. You just pass in two arguments: the exact file name you want to open and the mode you want to use. The mode is super important because it tells the compiler what your intentions are. Now, a quick note on error handling. If the file doesn't exist or your program doesn't have permission to open it, fopen will return a null pointer. You absolutely must check if your pointer is null before proceeding. Otherwise, your program is going to crash. C offers some very specific modes for different tasks. You use R if you just want to read a text file. If you're reading one of those binary files, you just add a B to make it RB. For writing, we use W. But be super careful here. Using W will completely overwrite any existing content in that file. If you want to keep your old data and just add to the end of it, you use A for append. Choosing the right mode is basically your first line of defense against accidentally deleting your own data. And here is an absolutely critical best practice. Once you are done reading or writing, you cannot just walk away. You must use the fclose function on your file pointer. This explicitly tells the compiler that you are completely done working with this file, allowing the operating system to safely save the data and free up the memory resources. If you forget to fclose, you're risking data corruption and memory leaks. Always close your files. Which brings us to Section 4, read in data from files. And hey, before we dive into the code, if you're finding this series helpful, don't forget to like the video and subscribe. If you have any questions, leave them in the comments. They might be answered in a future chapter. Let's look at reading a text file. To extract structured data, like an integer, we use a function called fscanf. Honestly, it acts exactly like the standard scanf you already know for getting input from the keyboard. The only difference is that you pass your file pointer as the very first argument. This just tells C, hey, don't wait for the user to type a number. Go read this integer directly from the file. But sometimes you don't have nicely formatted numbers. Sometimes you just need to read a file character by character. For that, you simply use fgetC, and it will grab the very next single character from the file for you. But how do you know when to stop reading? If you're using a loop to read characters, you need to know when you've hit the end of the text. This is where error handling is key. When fgetC reaches the absolute end of the file, it returns a special signal called EOF, which literally stands for end of file. By setting up an infinite loop, we can read a character, immediately check if it equals EOF, and if it does, we safely break out of the loop. It's a beautifully simple way to prevent your program from crashing by trying to read data that isn't there. Let's move on to Section 5, Writing Data to Files. Reading is great, but we obviously need to save our new data permanently too. To write an integer or any formatted text to our file, we use fprintf. Notice the pattern here? It completely mirrors the standard printf logic we use to print to the screen. But by adding that f at the beginning and supplying our file pointer as the first argument, we direct that output away from the screen and straight into our permanent file storage. And just as we have fgetC for reading single characters, we have fputC for writing them. If you just need to write one character, you use fputC, passing the character itself, like a lowercase c in single quotes, followed by your file pointer. Let's wrap everything up in Section 6, Review and Next Steps. We've successfully moved from the volatile world of RAM to the permanent safety of the hard drive, so here are your 5 key takeaways to memorize. First, RAM is volatile. You must use files for permanent storage. Second, the file pointer is your required bridge connecting the program to the file. Third, always specify your fopen mode carefully and make sure that pointer isn't null. Fourth, use your targeted read and write functions like fscan and fprintf. And fifth, the ultimate golden rule: never forget to fclose your files to free up those system resources. You now have the power to make your program's data outlive the program itself, which is a massive step forward. In the final chapter, we'll explore dynamic memory allocation, where programs can request and manage memory while they're running. It's going to be a real game changer. See you in the next explainer.